Welcome to Lecture 9, 1.3, Complex Numbers. So complex numbers, we're sort of broadening the range of numbers we've been working with before. We're including this new number field, which is called imaginary numbers. Now, they're not actually imaginary. It was a phrase sort of coined by other mathematicians who did not believe the mathematicians who were looking into these numbers. And the mathematicians who were looking into these numbers were Leonhard Euler and Carl Friedrich Gauss back in the 1700s. These numbers are being found. And other mathematicians thought it seemed imaginary, hence the phrase imaginary. And also why we call the number I for imaginary. Now, imaginary numbers actually are useful. We use them in real life, such as they appear in electricity or quadratic equations. They also could be used in signal processing, which is useful with cellular technology and wireless technology. Even in radar and biology, so like brain waves. So imaginary numbers are actually very real. It's just they unfortunately got coined imaginary numbers. Alright, so the definition after that very long intro, we have the imaginary number I is equal to the square root of -1. And I squared is -1. Now what makes this special? Well, previously, with all the numbers we knew, you could not square a number and end up with a negative answer. Because normally, for us, we have positive or negative numbers, like -1. If you squared that, you would get +1. Or, if you took +1 and squared it, you would still get a +1. You could never get a negative answer before with the numbers we were using. But Carl and the other guy found out this number. They identified it. You could say I squared does actually equal a negative number. And what else do we know? Well, if b is a positive number, then the square root of -b can be simplified into I square root positive b. So this is often how we will be simplifying things. When you see a negative under a radical, you will simplify it by bringing out that I and making the b positive. Okay, so oftentimes that is how we'll be simplifying. Let's take a look at some examples. Write the following imaginary numbers in terms of I. Well, when I see this, I see the square root of a number, which is asking what number times itself could give me a -25. Normally, this would not be possible, right? Because the only numbers we used to have would be 5 times 5 or -5 times -5, which would never have given us that -25. So normally, we would have said that this number does not exist. But Leonhard Euler and Gauss said, if we have the number 5i times 5i, it'll give us the -25. Why is that? Because the 5 times the 5 gives us the 25, and the I times the I gives us I squared, which, remember, according to our definition, is -1. And hence we would get the answer -25, which we were looking for the answer of our square root. So that's the long explanation there, but to simplify this, all you're going to do is split it up between the negative root and the 25. And we know by definition that the negative square root is equal to I. So we can simplify this out to be I square root of 25. And simplifying the square root of 25, we get I5, or oftentimes you write it as 5i. So you can go ahead and try simplify the next two. Check with me in a second. Alright, so this would be square root of -1 times the square root of 12. Square root of -1 is I, and let's see, can we simplify the square root of 12? Well, there is that perfect 4 in there, and then the leftover 3. 4 times 3 gives us that 12. So we can simplify this to 2i root 3. Alright, so normally, when you have a square root, the square root will always be last when you write it. That's just how it's normally done. I would end up being in between, and the 2 would be at the end. though there are some cases where you would write it the other way. But if you did that, make sure to really indicate where your radical ends. Okay. All right, let's take a look at this next one. So we have the square root of -1 times the square root of 50. That'll be square root of -1 times, let's see, 50 can be split in 2, 25 and 2, which would be I root 25 is 5 root 2. So that'll be 5I root 2. All right, let's take a look at this next example. Simplify the following expressions in terms of I. So the first thing you're always going to do when working in terms of I is you're always going to get rid of the negatives in the radical first. Do not just multiply straight through. Okay, when we do that, we'll get I root 9 times I root 25, which we can simplify into, well, the 9 simplifies into a 3, so I times 3 times I times, and the root 25 simplifies into 5. Then we can multiply the 3 and the 5, and the like terms of I, and we will get, let's see, 15I squared. But remember, according to definition, I squared equals -1. This was in the definition in the very beginning. So let's simplify that out. We get 15 times -1, which will equal -15. So note, it's always important to change from the negatives in the very beginning. Change those into I. Okay, try pause the video and work on the other two by yourself, or at least work on B by yourself, and check back in with me in a sec. Okay, so we'll have I root 10 times I root 2. Can't actually simplify those guys. So what I'll do is I'll combine the I squared, and then I'll combine the 10 and the 2 to get the square root of 20. Well, I can actually simplify the square root of 20. That is the square root of 4 times the square root of 5. And I can simplify 4. And lastly, you should notice we have that I squared, which we need to simplify into -1. So that'll be -2 root 5. And let's take a look at C. As usual, we want to get rid of those negatives under the radicals first. So that'll be I root 50 over I root 2. And we can go ahead and cancel out those i's. They're a like term there. And then we have 50, root 50 over root 2, which you can simplify into root 50 over 2, which will be root 25, which equals 5. Alright, so as usual, always get rid of the negative and turn it into an I first before you simplify. Now, so when you introduce complex numbers, there's actually going to be a way that's considered a correct form for how to write the answer when there's a complex number. So if you have an imaginary number included, what you're going to do is write the real number part first, which is what we call A. For example, any number you think of normally would be the real number. 1, 2, -5, 13, 2.5, etc. But once it starts to have the number I in it, or the letter, sorry, you need to include the imaginary part and the real number part. Let's take a look at the example. Simplify each expression and write the answer in complex number form, which is A plus BI. Well, looking at this, what can we simplify? Well, that root 100, that can be simplified. And actually take a moment, hopefully I fixed this in your notes, but that should be root -100. So to simplify that, we're going to go ahead and get rid of that negative under the 100. We'll have 3 minus I root 100. Then we can simplify the root 100. 3 minus I times 10. But we would not answer like this. Why not? Because the form for answering a complex number, you need to have the number part and then your imaginary. So we'll rewrite this. This is going to be 3 minus 10I. So in this case, when you have a real part attached with an imaginary number, that's when you have the I at the very end. And there we go. So for part B, let's see. Well, we can't, there's no radicals here to simplify. The only thing here is that we have simplified numbers over a fraction. So what we need to do is split the fraction from the regular number part. So I'm going to rewrite this. This would be 2 over 5 plus 7i over 5. Can I do that? Well, let's think back the opposite direction. If you had this side, and you started out with 2 5s plus 7i over 5, to add fractions, you need the same denominator. So you would keep the denominator and add the top. So keep the denominator 5, add the top, 7 plus I. Yep, that's okay. So we sort of decomposed, you could say, this fraction. And when we do that, we get the regular number part and the complex number part separate. So this is in a plus bi form. Okay, let's see for part C. This one, actually, we have a radical with the negative inside, so we need to get rid of that first. So this will be, let's see, negative 6 plus I root 18 over 9. Now, can I simplify that root 18? There is a 9 in there, so there's that perfect square, excuse me. 6i plus root 9 times root 2 all over 9. Can simplify that too. Negative 6 plus 3i root 2 all over 9. Once again, we'll do that trick of splitting the fractions. And we get negative 6 over 9 plus 3i root 2 over 9. Can we simplify anything? Well, the 6 and the 9 we can simplify, so that'll be 2 and 3. And then the 3 we can also simplify, 1 and 3. And we are left with negative 2 over 3 plus, oh, this is interesting, I over 3 root 2. So the question is, are we done? Can we box our answer? Technically, this is not in the correct complex form. Why? We need to have I at the end. So let's rewrite this last term. Root 2 over 3, I. Now you might ask, why are we putting I at the end there all the time? Well, in a lot of application problems, people want the I on the side because then you can easily pick out this number. And in application problems, like what I mentioned before, electricity and other random things where imaginary numbers do pop up, it's helpful to be able to just pick that number right out, instead of having to look at this mess and sort of figure out what the number is. Alright, so there we go. Writing it in complex number form, a plus bi. And for objective 3, performing operations on complex numbers, that is actually kept for Math 135, not Math 103. So that is it for our section here.